KIT. She'll be going to be talking about unimodular versus nilpotent superfield approach to pure DS supergravity. Over to you, Shruti.
Thanks, Pratik. And good afternoon to everybody. And thank you to the organizers for giving me this chance to talk on this topic. So this talk is based on some work that has already been done and some work that's still in progress with my collaborators, Sylvia Nagy, who is at Queen Mary University of London, Antonio Padilla at the University of Nottingham, and Yvonne Zavala at Swansea University. Okay, so I'll start now. As we all know, we have a lot of observational evidence telling us that our universe is expanding at an accelerated rate. And an accelerating universe is well approximated by the maximally symmetric solution of Einstein-Hilbert gravity with a positive cosmological constant, which means d zeta space-time. And if we try to look for a theory of pure supergravity, where by pure I mean a theory where you do not have any coupling with matter or scalar fields, then we see that linear supersymmetry in 4 dimensions for n equal to 1 supersymmetry, it only allows for Minkowski or ADS solutions, but not for d zeta solutions. So this is something that I can explain a little more explicitly using the algebras. Now, generically, the d zeta or anti-d zeta algebras, the main algebraic relation that we need to know is the commutator between the translation generators. The translation generators don't commute, but they have this non-zero Lorentz generator sitting here. And there's this constant S whose value depends on whether the solution is d zeta or anti-d zeta. So it's -1 for ds and +1 for anti-ds. And here, this is the algebra for n equal to 1 4-dimensional supersymmetry. Now, when we try to embed the ds or ads algebra with into this linear SUSY algebra, which basically means combining this commutator with this one, and then when we try to satisfy the Jacobi identity, we find that the value of this constant S is fixed to +1, which corresponds to ADS spacetime. So we see that linear n equal to 1 supersymmetry does not allow for d zeta solution. So the solution for this is that we go to nonlinear supersymmetry, and pure d zeta supergravity was constructed by realizing an n equal to 1 supersymmetry nonlinearly. And it was done for the first time by Berkshire and collaborators in 2015. But soon after, there were some other groups who came up with very different methods of constructing essentially the same action. So the first method was Nilpotent superfields. The other one was Goldstino Brane action. And the third one is Stückelberg unimodular supergravity. I will briefly explain all of these methods. So the main things or the main points that motivate this talk are, firstly, what are the different methods for realizing supersymmetry nonlinearly? And once we have the different actions, we would want to know if they are physically the same or if they are actually different. And since these actions can be quite complicated and ugly, it's not so easy to compare them. Also, since they are being constructed by different groups of researchers, they have their own conventions and notations. So it's not so easy to compare these different actions. So I will talk about how to compare these actions. Okay, so here I'll give a brief historical review first. Pure DS supergravity was constructed for the first time in 2015 by these people, Berkshire, Friedman, Kalosh, and Proyan. And they did it using nilpotent superfields and superconformal methods. And soon after, which was later in the same year, there was this other group of people in Padua, Pandos, Martocci, Sorokin, and Tonin, who also gave a pure DS action, but their method was quite different. What they did was they took something known as a Goldstino 3 brane, and they coupled it minimally to supergravity. Now, these people used Weil spinners, whereas these people used Majorana spinners. I'll come back later as to why I'm saying this. After that, a lot of other work has been done in d zeta supergravity in recent years. Here are only some of the names. I couldn't include all the names in just one slide. So they have done things like studying properties of nilpotent supergravity and scanning the supersymmetry breaking scale and the gravitino mass in pure DS supergravity, and coupling pure DS supergravity to matter and other such things. And there have also been many inflationary models that have been constructed in pure DS supergravity. So it has also found many applications in cosmology. And though the immediate focus of our work is in supergravity, one of the long-term motivations of this work is to seek de Sitter vacua in string theory. And when you talk about de Sitter vacua in string theory, the first thing that comes to your mind is KKLT mechanism. And one of the key ingredients of that mechanism is the uplift from an ADS vacuum to a de Sitter vacuum by introducing an anti-D3 brane. And in recent years, a lot of work has been done that has made progress in explaining the role, like clarifying the role of that anti-D3 brane, and it has led to the construction of many different brane models. So here's a brief outline of the things that I'll be talking about. First, I'll give a brief description of the first type of action that was constructed for pure DS Sugra by Bergshoff and collaborators, and then by the second group, Bandos and collaborators. Then I will talk about the third type of action, which was constructed by my collaborators. But to explain it well, I'll first give a description of a simpler case of unimodular gravity. And then once I've explained how all these different actions are constructed, I will try to show how to compare them. And then this action that I will show here will be only up to a certain order in fields. And so then I will talk about some work that we are doing at present, and then I'll close with discussion stuff. Okay, so this is a very schematic description of the first model for pure DS supergravity. And the authors of that paper, they start with 3 different multiplets. The first one is called a chiral compensating multiplet. It has these components. This is a scalar field, this is a fermion, and this is another scalar field. And then this is the nilpotent chiral multiplet, and this is a Lagrange multiplier multiplet. So always the first and third components are scalars, where the middle one is a fermion. And this is a schematic form of the Lagrangian. You don't need to understand very carefully right now. The main thing to see here is that there's this superpotential W, and it has this expression where these constants A and B are arbitrary. And the Lagrange multiplier sits here. Till as long as this Lagrange multiplier is present in the Lagrangian, supersymmetry is realized linearly. But since we want to break it or realize it non-linearly, we solve the equation of motion of lambda and we eliminate it. So what we do for that purpose is that we first take this nilpotent chiral multiplet S, which as a superfield, it looks like this. So the fermion sits with theta, and the last scalar sits with theta square. And then we apply the nilpotency constraint, which is basically just the square of this superfield is 0. And that gives us this relation between the scalar field and this fermion. So using this relation, we can eliminate the scalar field from the action. And once we do that, this fermion gets recognized as the Goldstino because in nonlinear supersymmetry, a fermion doesn't necessarily transform into another particle, which is a boson, but it transforms into a bosonic superpartner, which is composed of the same fermion itself, and that's what's called the Goldstino. If I get some more time, and this is like the basis of the construction of a Volkover-Coulomb action. If I'm left with time, I can elaborate more on it later. So once we do this and we use the equations of motion and find the solutions, the cosmological constant takes this value in terms of these constants, which were present here in the superpotential, and I said that they are arbitrary. So now, depending on which of A and B has a higher value, we can have both a positive and a negative or even 0 value for the cosmological constant, and hence we see that this theory allows for de Sitter solutions. So this is how, this is a very basic explanation for how nilpotent supergravity works. Obviously, when you do the calculations, there are lots of other things to consider.
Supergravity, can I ask you a question? So A and B were complex. You allowed them to be complex?
I'm not sure actually. I can look it up. I don't know. I'm sorry.
Okay.
Why do you
And
think will it have any
I'm just
effect?
asking. No, and I'm just asking. The other thing is that if the supersymmetry is realized non-linearly, would your
Yes.
solution still be stable?
Yeah, we checked for the stability.
Okay. Okay, thanks.
Sure.
And was this guaranteed? I mean, was this guaranteed a priori? I mean, did you check by constructing fluctuations, the quadratic fluctuations around the solution?
Yes. I mean, since this is not our action, we did not check it particularly for this action obtained by Nilpotent superfields. But my collaborators and I worked on Super-Stückelberging of unimodular gravity, which essentially gives the same action. And over there, we studied the fluctuations, and we found that the solution is stable.
Okay. Okay, thanks.
Sure. Okay, so now I come to another method of constructing pure DS supergravity, which was given by these people, Bandos, Martucci, Sorokin, and Tonin, and they're all in Padua. So again, this is just a schematic explanation. Here, the action can be considered to be divided in two parts. The first one is just a standard supergravity that was there earlier, and then this is a new addition, Volkov-Akulov action, which gives the positive part, which corresponds to this action. So the first piece is given like this. Here, this is the standard pure supergravity piece. Here, kappa square is Newton's constant, and this z is a coordinate, which it's like it exists in the whole superspace. So, which means there are 4 space-time coordinates, 2 chiral coordinates, and 2 antichiral coordinates. So that's why you have 8 coordinates in total. And here, this E is some kind of an invariant one form, and you take the Berezing, and that gives you, it's like just integrating the volume element. And then the second part gives you the negative cosmological constant term, or the ADS part. Here, this is only in the chiral subspace. So that means you have the 4 space-time coordinates, and then you have 2 chiral coordinates. And here you also take the Hermitian conjugate. So this is the ADS part, and then we come to the supersymmetry breaking part, which gives you the positive contribution to the cosmological constant. Here now, this is called these coordinates, xi. They are the 3 Brane world volume coordinates, and that Brane is dubbed as the Goldstino Brane because it eventually generates the Goldstino. And this Brane is coupled to supergravity by embedding these coordinates in the superspace coordinates like this. And here, this E, again, it's the one form which is invariant under all of the transformations, all the supersymmetry, supergravity transformations, and then you take the superdeterminant, and that gives you the Volkov-Akulov action. So now, these people, when they computed the equations of motion, they saw that for the auxiliary fields, those fields belonged to nilpotent superfields. So even their method involved superfields directly in some way. Though eventually they found that their action is equivalent to the action provided by Bergshoff and collaborators via field redefinitions. So when we put up the action, the Goldstino Brane action given by these people, up till the 3rd order in fluctuations, this is the form of the action. Now, you don't need to look at it very carefully or closely at the moment. Maybe you can just look at 2 fields present here. One is this one, G Karen, which is the Goldstino, and another one is psi nu, which is the Gravitino. I am showing it here right now just to give an idea of what the Goldstino Brane action looks like. And I will come back to it later again. So I have explained briefly the 2 different methods by which pure DS supergravity was constructed in 2015. And now I will explain a completely different method, which was found by my collaborators. And it's called Stückelberging unimodular supergravity. But in order to help you understand that easily, I'll first give a simple example of unimodular gravity. So this is what a unimodular gravity action looks like. The first term is a simple Einstein-Hilbert action. And then the second term contains this Lagrange multiplier field, lambda of x. And when we solve its equation of motion, we get this condition. So it's like a constraint on the determinant of the metric. And this constant epsilon naught, it is usually set to unity. And that's why this action is called a unimodular action. So now this unimodular gravity is like a gauge fixed version of Einstein gravity. And both of the actions are supposed to have exactly the same solutions. The main difference being that in Einstein gravity, the cosmological constant appears as a constant to begin with, but over here, you take the vacuum expectation values of the Lagrange multiplier, and then that you get the cosmological constant. So sure, we added this term here, but this term, lambda epsilon naught, that's present here, it breaks the diffeomorphism invariance of the action. And that is a very important symmetry. So we can't continue with an action which does not have diffeomorphism invariance, and we need to restore it. The one thing to note here is that this full action is still invariant under a set of subset of diffeomorphisms, which are called transverse diffeomorphisms. So the diffeomorphism symmetry has been broken, and now we want to restore it. And for that, we use what's known as a Stückelberg procedure. Now, for that, like when we perform diffeomorphism transformations, we can do it in two ways. Either we can do an active transformation, which means we transform the fields and let the coordinates stay as they are, or we can let the fields stay the way they are and perform the transformations on the coordinates, which are called passive transformations. So first I'll show the active transformations. The field lambda transforms under active diffeomorphism transformations like this. Here, xi mu is a transformation parameter. So these are infinitesimal transformations where I've only shown the first few terms. And when this field lambda transforms like this, the action there, all of these terms are the extra terms which are not present in the action before the transformation, and so they are breaking the symmetry. So in Stückelberg procedure, what we do is that we take this transformed field and we let it sit in the action. Over here, so here you will see that there are derivatives acting on lambda, but if you do some partial integration by parts, then you can take lambda out such that the derivatives sit only on the xi's, and then the transformation parameter xi mu is promoted to a field phi mu, and the field phi mu is now called the Stückelberg field. So this is the Stückelberging procedure where the transformation parameter is promoted to a field. And now in this action, if we transform, if we do diffuse, then lambda will still transform like this. But now since phi is a field, it will also transform under diffuse. And its transformation is such that all of those extra terms coming from the transformation of lambda get canceled by the extra new terms coming by the transformation of phi. So this way, the action becomes invariant under diffuse.
I have a question. I mean, you said that the equations, I mean, the equations of motion or the solutions to equations of motion of this gravity theory is the same as the normal one without that constraint. Is that true? I mean, like if you look at the ADS vacua, the root G is not a constant, right? I mean, it's a function of R. So ADS vacua solves
like a gauge fixed. It's a gauge fixed version of GR.
Yeah, but root G, I mean, like if you just take this ADS vacua and you calculate root G, root determinant G, that's not a constant, certainly.
No, this action is anyway not diffuse invariant. It's okay. I think so. It's like when you find the full diffuse invariant action, then that's equivalent to GR, to Einstein gravity.
Oh, okay. So this is not, I mean, this theory is not equivalent to Einstein gravity.
Yeah.
Okay.
I mean, no, because this is not even diffuse invariant. Yeah.
Yeah. So solutions to Einstein's gravity need not be solutions to this theory.
Yeah. I mean, I'm not sure if I would even call it a consistent theory because it's kind of incomplete at this stage.
Okay. So that statement is not correct.
Maybe I didn't say it correct, or I didn't say it at the right time. I probably shouldn't have spoken at this, like just after showing this action, but after showing this one. Okay.
Okay, go ahead. Yeah.
Okay, so here I showed active transformations where the field was transforming. Now I'll show the passive transformations. So again, this is very schematic representation. So I'm just showing that the coordinate transforms, x mu transforms to x mu hat, and then it's promoted to a field S mu of x by the Stückelberg procedure. And you must be knowing that when you transform the coordinates, and then when you write the Lagrangian with the transformed coordinates, you have to write the Jacobian and the determinant of the Jacobian. So we get this thing over here in the Lagrangian. And one can check that even this is invariant under diffuse. Okay, so this is how unimodular gravity works. And now unimodular supergravity is quite analogous, at least in the first few stages. So here, this is the n equal to 1 supergravity action to begin with. This curly epsilon is a volume element superfield, which is like analogous to square root minus g in Einstein-Hilbert gravity. And this curly r is also a superfield that's analogous to the Ricci scalar. So this superfield epsilon has these components F0, F1, and F2. And they are further written in terms of these fields. Here, E is the determinant of the V alpine, psi mu is the gravitino, and here capital M is a scalar field. It's an auxiliary field. And here are the components of the chiral superfield R. So it has the same field M, and then there's this new field, vector auxiliary field B mu, and here this is the Ricci scalar. So these are just the ingredients that are going into giving the n equal to 1 supergravity action. So now when we want to write the unimodular one, we bring in this Lagrange multiplier superfield, as you saw in unimodular gravity. And so now there's this constant superfield epsilon naught, and there's this volume element sitting here. And when you vary over lambda, you get this epsilon equal to epsilon naught. And this epsilon naught has these components. So its spinor component has been set to 0 for simplicity. So it only has the lowest component and the theta square component. And these are the components of the Lagrange multiplier superfield. So when we vary over lambda, we get this condition. And as in the case of unimodular gravity over here also, this last term, which is lambda epsilon naught, it breaks the diffeo invariance. But this time we also have supersymmetry. So there are actually both the symmetries are getting broken. This action is still invariant under a subset of diffeomorphisms as before. But now we have two symmetries to restore. And I mean, though initially the symmetry breaking part is lambda epsilon naught, but when you multiply these superfields and write out all the components explicitly, these are the terms which break the symmetry. So now again, in order to restore the symmetry, we use the Stückelberg trick. Now this was the xi mu is the diffeo transformation parameter, and epsilon is the supersymmetry transformation parameter, and these parameters are promoted to fields phi mu and zeta. And then when you transform the fields in the Lagrangian and then promote those parameters to the fields, so the Lagrangian that you then get is a completely invariant Lagrangian, both in diffeos and in supersymmetry, supergravity. And so yeah, that gives you a Stückelberg unimodular supergravity Lagrangian. Now over here, since we are doing transformations infinitesimally, where we take only the first few terms of the transformation, because the terms go on infinitely and we can't work with all of the terms. It'll be just too complicated. So we truncate our transformations up to a certain order in the field. So we are, all of this I show is up to the second order in the Stückelberg fields, and also the second order in these transformation parameters. And yeah, there was also these components of the Lagrange multiplier superfield, and these are the boundary conditions they obey. So the spinor component just goes to 0 at infinity, and the zeroth and the theta square components, they go to constants. And when we do this whole Stückelberging procedure, it's not only the Lagrangian that gets modified, but also the boundary conditions like this. Now, it's all quite complicated to look at, and you won't be able to understand much just at the first look. And there are all these fields and parameters. No, here only fields appearing. And
So
they're
the
given.
Lagrangian is also constructed to order by order and Stückelberg fields, is it? I mean,
Yes, right.
Can I see the? I mean, are there higher derivative terms in the Lagrangian, or
there will be? There are terms up till the leading order derivative in the Goldstino. No, there are no higher derivative terms as such. Okay. Even for the Gravitino, there are only leading order derivatives.
I mean, even if you go higher orders, I mean.
Well, no. Up till the second order in Stückelberg fields, you don't have higher derivative terms. But if you go a higher order in fields, then you'll have higher derivative terms.
Okay. Thanks.
So sure. Yeah. Anyway, so there are these functions like y1, y2, gamma 1, and gamma 2 appearing in these.
Yeah, I have a question. Sorry to interrupt you.
No
if you have higher derivative terms, I don't know if you're going to discuss this, but what is the status of ghosts?
So yeah, we believe that these higher derivative terms might be ghosts. And so at least up till the order of fields that I'm going to show in these slides, we don't have higher derivative terms, so we don't have any ghost fields. Actually, I will come back to this question later, and so I'm not sure if I should discuss this now, because I would have explained some more things before I come to that point. If by the end, you can bring up this question.
To discuss ghosts or lack of.
Sorry, what?
But you are going to discuss ghosts or their lack of.
Yeah, I will.
Okay, thanks.
Sure. So yeah, well, there are these functions, complicated looking functions, have such long expressions, and all of this goes into the, the boundary conditions and the Lagrangian. Question? Okay. So once we have the Lagrangian, the natural thing to do is to write down its equations of motion and solve the equations of motion. So the equations of motion admit this set of solutions. Here, the vacuum expectation value of the metric is G mu bar. It's the background metric. The Web of the scalar field capital M, we denote it as small m. And these are for the Lagrange multipliers. And from the solution, we can see that the cosmological constant takes this value. And here, K2 and K0 are arbitrary. So the cosmological constant can be both positive or negative. And this is how we see that this theory allows for d-zeta solutions. So I have shown now the construction of the Stückelberg unimodular supergravity action, which gives us d-zeta solutions. Now, if I try to compare it very schematically with the Goldstino Brane action, which was given by Bandos and collaborators, this one was given by my collaborators and me. So the first parts of these actions shown in green, they are the standard ADS parts, and they are exactly the same. But the parts shown in black, they are the ones that break supersymmetry and give the positive contribution to the cosmological constant. And at least at this stage, when we are looking at the schematic forms, they look very different. And it's not easy to compare them and figure out if they are the same or not. So we need to look for different ways. And what we do is we resort to perturbation theory. So we fluctuate the fields. These are the fields that went into constructing the Stückelberg unimodular supergravity action. And we fluctuate them around the background. And this is the metric. It's fluctuated around its background value. And the first order fluctuation is given by h mu nu. This is for the spin connection. And there are a couple of fields which vanish in the background, like the Gravitino, the auxiliary vector field B mu, and lambda 1, which was the spinor component of the Lagrange multiplier, and the two Stückelberg fields, phi mu and zeta. So these are the perturbations of the fields, and now we plug them into the Lagrangian, and we write the Lagrangian or the action perturbed up till the second order in all of these fields. And here, for simplicity, I'll show only the fermionic part of the action. Now, this is what the action looks like after performing the perturbations. And if we look at it a little closely, there are these bracketed expressions appearing. And here it's coupled to the Gravitino. So we can identify this as the Goldstino, so I denoted by the letter G. And the mode orthogonal to it is denoted by tau. So after performing these field redefinitions, when I rewrite the action, this is what it looks like. And the fields tau completely decouple from the fields G, which was the Goldstino. And it's also possible using the boundary conditions to completely eliminate the field tau. It vanishes at the boundary. And so we are eventually left with this action for the fermionic part. And this is the same as the fermionic part of the action that was derived using the Goldstino Brane by Bandos and collaborators. So at least up to the second order, over here, I have shown that the Stückelberg Unimodular Supergravity Action matches the Goldstino Brane action. And I had already mentioned it earlier that the Goldstino Brane action was shown to match the Nilpotent Superfield action via field redefinitions. So if we show that our action is equivalent to any one of the actions, it means it's equivalent to both of them. And so these are some field redefinitions I do on the boundary conditions, just to improve the appearance. And okay, so then I do the third order perturbation, and the Lagrangian that we get is like really big and very complicated and ugly, and it doesn't look anything like the Goldstino Brane action or the action that was obtained by Nilpotent superfields. So what we do from here on is that we try to find ways to simplify, and for that we first perform some field redefinitions. So there are all these auxiliary fields present in the Lagrangian, like the vector field and the scalars m, and then these are all the Lagrange multiplier fields. We do certain field redefinitions on them like this, and then when we compute the equations of motions for these fields, we get very nice solutions. Oops, yeah, we get very nice solutions. So up to the second order in fields, all of these fields vanish. So that provides us huge simplification. And when we eliminate all these auxiliary fields from the action, this is what we are left with. So this is the Super-Stückelberg action perturbed up till the third order in fields. And it is exactly the same as the action, the Goldstino Brane action given by Bandos and collaborators. And I had shown it initially when I was talking about their action. So this is quite a remarkable result that given how different the starting points for these different constructions were, all of these actions, they turn out to be the same, at least up till this point, only till the third order in fluctuations, but still. And here, if we look at the derivatives, there are terms which are leading order in the derivatives of the Goldstino. We don't have any higher derivative terms, at least till this level of fluctuations. And we believe that if we have higher derivative terms appearing, they might be ghost fields. For example, in principle, a de-Sitter action is not supposed to be, it's not necessary to be unique, because there are some terms like this one, which is given by Volkov and Soroka, which can also sit in the action. Like they satisfy all those invariance requirements that we need, nonlinear supersymmetry and minimally, it's not coupling to any scalar fields or matter. But these terms, they do not arise in any of the three actions that I have described. And so we believe that these fields might be ghost fields, which is why they are not showing up. And the fact that such potentially pathological terms are not showing up in any of the pure DS actions that have been constructed, it indicates that all of these three actions, they might have some common underlying origin, some more comprehensive theory, like at higher energies, some string theory model. And it would be interesting to figure out if there is such an underlying theory. Okay, so once we've seen that these actions match up till the third order in field fluctuations, the natural question to ask is, what about the comparison at higher orders? And so the reason why we had to do the perturbation up till third order in fields and we were going order by order was that we were doing infinitesimal transformations. And there were two types of transformations that we were applying. One was the planes Diffie transformation. Here, this is the Diffie generator. And then there's this other transformation given by delta S, which transforms the supergravity fields only, and it does not act on the Stückelberg fields. And this field lambda, it's supposed to transform as a scalar, which means it's supposed to obey this rule, where xm prime is this. So yeah, so as long as we work infinitesimally, we can only work with a certain number of terms. So we need to find some rules or some formula for doing finite transformations. And that's what we are working at now. Since we have two different types of transformations here, it's not so easy or trivial to find an operator that will transform all the fields at once. But we have done some calculations and some derivations, which gives us strong reasons to believe that we can use this operator here, which is quite easy to look at. I mean, it's simple that you just sum the two operators and you transform the fields. But it's not so trivial because you have to check the commutation relations and other things. So here we think that this field, for a finite transformation, it might transform like this, but it is yet to be verified at higher orders. And so if we find that this is how the fields transform under finite transformations, then we can again perform the Stückelberg trick as usual and write the action, the Stückelberg unimodular supergravity action up to all orders, like the full exact action. Now, even when we were writing the transformation rules for the Stückelberg fields phi, mu, and zeta, the transformations were only infinitesimal up to a certain order in the fields and parameters. But now for the Stückelberg fields also, we need to find what the transformation rule for finite transformations would be. And it's getting a little too complicated at the moment, but we hope eventually we can get some simple expression. And so this was this is all active transformations, and now I will talk about passive, in which we transform the coordinates. So this is the Diffie and supergravity transformations acting on the coordinates, and it's possible that the finite transformation is given by this formula. And we do the Stückelberging, which means we promote the parameter to fields. And again, I've shown this action before. This is just a schematic form of the action. So this is what it'll look like. But it's important to know what the Berezinian actually is like. I can just write that this is the Berezinian and it's the superdeterminant of the super-Jacobian matrix. But what does it look like? So this is the super-Jacobian, and a little more explicitly, it looks like this, where the transformed Stückelberg field phi m is you have its derivatives with respect to the super coordinates like this. And this is the formula for computing the Berezinian of a super-Jacobian. And it can also be represented like a superfield like this. But when you actually have to compute the Berezinian, it's not that straightforward. One important motivation for wanting to work with this passive transformations is that this Stückelberg unimodular supergravity action, it closely resembles this type of action, which is called a Hanau-Teitelbaum action because it was first given by Hanau and Teitelbaum in 1989. It's very similar to the unimodular supergravity action, except just the fact that here, instead of a constant, you have this total derivative of a field. So what we are aiming at is to write this term as a total derivative so that we can bring in three forms into the picture. So here, by doing some integration by parts, I can transfer this derivative from tau to lambda, and then like write it in terms of another field A, which is a 3-form dual to tau. And now 3 forms are ubiquitous in flux compactifications. And if we try to uplift our action to from a 4-dimensional theory to a higher dimensions, then 3-form supergravity is the most suitable form, because the field strengths of 3-form gauge fields can be identified as duals to the fluxes that thread the internal compactified space. So all of this provides us motivation to write our Stückelberg action as a Untitled action. So basically, to write the Berezinian like this, where here this field Tm, where this index capital M, it can take values mu, which are for Lorentz indices, and alpha for spinor indices, and these are the components. So we have managed to find what this field Tm will be like up to a certain order. And we think that it might be possible to write a formula for higher order terms, like a general formula, such that you can tell what the term at any given nth order would be. And this is the transformation rule for the field Tm. So we need to ensure that this rule is being obeyed for consistency. So yeah, so basically we are trying to find the full or exact form of the Stückelberg action up to all orders using 2 different methods, both active and passive transformations. And once we manage to find that action, then we can compare it with the Goldstino Brane action or the Nilpotent superfield action up to all orders. So if it turns out that all the 3 actions are equivalent up to all orders, it will provide us strong grounds for believing that they come from some underlying theory, I'd say at higher energies, like some string theory model. If, however, we find that they have differences at higher orders, even though they matched up to the cubic order and field fluctuations, then it will indicate some fundamental differences, and it'd be interesting to explore the phenomenological consequences in greater detail. Now, when I talk about the possibility of a string theory model, it's worth mentioning that such a model was already shown in this paper by the same people who showed the Goldstino Brane action. This was a paper following their Goldstino Brane action paper, where when they coupled their pure ds supra action to matter and took special cases of that action, they showed that it matched the 4D effective action for an anti-D3 brane that was coming from the flux compactifications of 10-dimensional type 2B sucra, which was constructed using the KKLT method. And the anti-D3 brane was confined at the bottom of some strongly warped throat. So that's quite an interesting result. So it already is giving us indications that this pure DS action that we are working with, it has some kind of counterparts in string theory and 10D supergravity. So yeah, I would be interested in, once we finish the whole construction and analysis and comparison of these 4-dimensional actions, I'd be interested in uplifting it to 10 dimensions and also try to find the string theory counterparts. And another thing that can be done is to find inflationary cosmology models using these pure d zeta supergravity actions, because that field is quite active these days, and it seems to be giving some interesting results. Yeah, that's all I have. Thanks.
So I came a little late. I was wondering, what are these uses? I mean, what these actions have been put to some use or some, I mean, what have they been used for? I mean, because you're spending a lot of effort constructing them. So
okay, so the primary motivation is I mean, it's a long shot, but maybe it will explain the accelerated expansion of our universe. That's the main reason that motivates any kind of d zeta constructions.
Right. But I mean, okay, okay, maybe I don't know some basic, but this de Sitter has a vacuum energy, positive vacuum energy. So how does how is it consistent with supersymmetry? Because it has to be broken, is it somehow?
Yeah, exactly. We have broken supersymmetry.
Huh. So you have some, I mean, just because I came late, you have some supersymmetric models, and then there is some, some vacua which has positive energy, and that's where the de Sitter vacua occurs. Is that?
Yeah. So I don't know. At what point did you join?
I don't
Like,
know,
so that I
maybe
can.
10, 15 minutes later. Sorry, I have to do.
No, it's okay. I'm just trying to see if I can show you an action that shows. Yeah. So, for example, you can look at this action. This is the Super-Stückelberg action. Now, the green part is the already existing ADS supergravity, which you can also have with just linear supersymmetry. But
Okay.
this is the supersymmetry breaking part, which gives the positive contribution to the cosmological constant.
Okay. Okay. And okay, you are interested in supersymmetrical models because somehow they are controllable, and maybe you can hope to get some exact result, or
I mean, it's nice to see that using supersymmetry or supergravity, you can get pure DS solutions, pure D Sitter. So when I say pure, it means a very minimal model in which you're not coupling to matter or scalar fields, which generally makes the model phenomenological, and then it's a little too tweaked. But if you're looking for something general, then I mean, a pure Lagrangian without any couplings can be quite promising, because you can do a lot of different things with it, which you can't always do with a Lagrangian that already has fields to begin with, matter or scalar fields, I mean.
Okay. Thanks.
Yeah, did you comment about the ghosts? You said you were going to say about what happens to the ghosts when you have higher derivative terms at the next order that you.
So okay, yeah. Maybe I didn't explicitly talk about the higher derivative terms. Okay, one thing that I said here was that at least in this Lagrangian that is up till the cubic order in fluctuations, you only have leading order derivative terms, and there are no ghosts here. But if there were any higher derivative terms, even if higher derivatives of Goldstino, we believe those are ghost fields. And there are some terms which can in principle exist in the Lagrangian because they obey all the invariance rules and they keep the action minimal. That means they don't bring in any new fields. But these terms did not appear in any of the three actions. So we believe that they are ghost fields, and as in these pure DS actions that we're constructing, they probably have some underlying model like that's connected to string theory. So it means that it has some kind of a physical relevance, which will be ruined if you had ghost fields in the system. And that's why these ghost fields are not appearing.
So if I understand you correctly, you're saying that there are no ghosts up to the order that you have derived.
Yes.
But if you go to next order, there will be higher derivative terms. So there is a good chance that ghosts will appear. On the other hand, you also believe that this model is embeddable in some kind of a string model, and in string models, if done right, are consistent. So there should be no ghosts. Did I understand you correctly?
Okay. You understood me correctly for the most part, but when you say that if we go, that my action that I showed was up till third order fluctuations, and if we go to a higher order of fluctuations or fields, then there will be higher derivative terms and they will be ghost fields. This is something that I cannot agree with. I am not sure that if you have higher derivative terms at higher orders, they will be ghost fields.
I mean, generically they give rise to ghosts, and you have to work very hard to show that higher derivative terms and higher derivative gravity theories have no ghosts. It is not at all obvious.
Unless and until you want to think of them as effective field theory. So is there a scale in your Lagrangian which is in front of these higher derivative terms?
Yes, there is. Yeah, here, this lambda 2. This is the
Yeah.
supersymmetry breaking scale.
Okay, so this might be, so in some effective field theory sense, maybe these higher derivative actions could still be sensible. But yeah, what Sachin is saying is of course correct. I mean, if you have higher derivative terms, then your propagator typically gets modified. It'll morally speaking look like something like 1 over p to the power 4 plus 1 over plus p square. And if you split it into partial fractions, you'll see two kinetic terms of different signs. So you will generically have ghosts.
Can't escape ghosts generally if you have higher derivative terms, unless there is some miraculous cancellation.
Yeah. Or you
Which is
think of
not
them
obvious.
in an effective field theory sense in which you say that this theory is only valid up to a particular scale. I mean, that is one way of, and the ghost excitation is beyond that scale. That is one way of avoiding contradictions.
Okay.
The other question I have is, I mean, why are you? What is the reason that you have to be optimistic that this is embeddable in a some version of KKLT, either KKLT itself or one of its various cousins?
Okay. I'll just go back to the slide. So there are two reasons. First reason being that since all of these different supergravity actions are, at least up to this stage, are coming out to be exactly the same, it seems that they have some underlying theory. And when you think of underlying theory, you will think of something, that's probably valid at high energies. And that's why I think that there might be a string theory model. And the second reason is that in this paper, which was the paper following the Goldstino Brane paper, the authors have shown that when they couple their pure DS supergravity to matter, it has special cases which match the KKLT type action.
Okay, so if it is embeddable, then would one say that in your work, the vacuum that you are looking at at least to second order is only a metastable vacuum then? The d theta is a metastable vacuum?
Can't comment on that yet. I mean, I know that in KKLT you have a metastable vacuum, but though we have seen
I mean, if they are embedded.
So yeah, like though we have seen some correspondences with the KKLT like action in string theory, it's not necessary that if we do find a string theory model for this pure DS supergravity, pure DS supergravity, it will be a KKLT type model. It might be a completely different string theory model, and so it doesn't have to have a metastable vacuum like KKLT.
But this is an expression of.
Sorry, I can't hear you. I can't hear.
Sachin, you broke off, I think.
His internet connection went.
Okay. I think it was expression of hope. That's what I guess.
So regarding stability, at least till as long as we did the field fluctuations up to the cubic order, everything was stable and good.
I'm sorry, there was a internet disruption at my end. So I missed missed about the last 10 seconds of your reply.
No, actually, we couldn't hear you. I think.
No, yeah, we didn't hear your question.
You didn't hear my question. Well, all I was saying is that is there any when you say that there may be other models where this might be embeddable in some other string model where the vacuum is unique. Did I understand you right?
Yeah. So yeah, I mean, yeah, I think you're talking about a metastable vacuum because you're thinking that we are trying to connect it with the KKLT construction. So yeah, that's what I'm saying, that the KKLT model is only one possibility, but it's not the only string theory model that we would be able to connect it with. Maybe it's a different string theory model. I don't know.
Okay, I think I understand your point.
Okay.
Okay, probably if there are no questions, then maybe Sachin, Justin, and I can have a word with Sukruti, and the rest can leave. And Pratik, you can stop recording.
Yeah, I've stopped the recording.